purpose, and I have to say this really come across the ranges of applications that have been, let's say, encountered. It's been really also about, let's say, having ways that one could get to higher image quality, better spatial resolution, and in this respect, let's say, requests for better locating performance, better, let's say, detection. Usually, I rather say imaging, because it's not only the detectors that we have here. Ways to automatically correct for imperfection of the image in the existing cases, but also isotropic voxels and larger volume data sets. So here I'm going to take these different points and show you also tracks, let's say, that are being worked on or released lately to address those. One which I will only spend one slide on. Obviously, let's say, probably a difficult one in a sense that it has really to do with core, let's say, technologies, and where, let's say, we are still very actively working on the platforms themselves, including the DualBeam, keeping, let's say, the 3D applications in mind, and see how, let's say, from a column point of view or a detection point of view, we can actually improve the quality of the data to your 3D application. And in that respect, especially as far as DualBeam is concerned, let's say the latest step has happened only a couple of weeks ago. Let's say when let's say we've actually launched let's say a new platform where let's say we definitely have worked quite extensively both on the locally imaging, on the detection, and on techniques to reduce drift actually on imaging to really boost the performance, and which obviously becomes immediately applicable to 3D. But then, so that was, you could say, more, let's say, working on the core technologies. The other part of the work really go directly to the automation, and to address a number of points that can immediately improve, let's say, the data set. Starting with dynamic corrections of focus of estimation, for instance, automatic centering of the region of interest, that will also save time in the construction. Then also improving on the Z direction, and let's say, especially with respect to slice placement. And let's say more recently, which is the latest part here, go towards larger volume, let's say, correction for drift as well as part of the 3D. And let's say, since we're also talking, and I've heard that already this morning many times, of work that may last 2 to several days in automated mode, ways that the tools can also be operated efficiently in remote operation, so that at least during the weekend you don't have to lock yourself in the laptop. I've heard it. So when it really comes to the Z resolution, I mean, the things that was done, I mean, some of it you could say is pretty obvious. It's been about, let's say, also introducing fiducial marks so that, let's say, one could accurately position the beam when cutting. And this is an extra security, if you will. Do not assume that your beam is at the right place, but verify that it truly is there. And then here we've got again the complete acquisition top down with a fill here with every slice that has been automatically repositioned and cut, and then the resulting SEM image. So we have, let's say, this min, but let's say we have an additional, let's say, element, let's say, to guarantee, let's say, the quality in the Z direction, which is, let's say, a tool that will automatically also measure the distances between each individual slice. And this is something which we actually get here, so it was plotted here, let's say, on this graph. And if I'm taking the data set which I have here, so where I had a pixel size of 0.5 nanometer, and a pitch in Z, so a distance between each side of 10 nanometer, I can actually really measure an average distance, which is a good match with what was actually targeted, as well, let's say, as a way to measure the deviation, whether standard or 3 sigma. That's not true to the kind of metrologies that one expects. Then correction of drift, also just to explain very quickly about what is available here, that's really built in the DualBeam, and which really allows to on-the-fly correct for drift by means of, let's say, image realignment. And practically what this means is, let's say with the traditional scanning, I'm experiencing drift, for instance, related to charging or the stage, I can get back, let's say, to completely strong images. Moving very quickly also to larger volume, say also here a couple of thoughts have been put there, and say the strategy that was chosen for here is really to offer the ability to collect multiple frames within a slice, so that really large images could be collected at higher resolution, but with little impact from the drift. And so here, what you see here, I mean, each tile has already a certain definition, but then we will add them all. And let's say as part of the reconstruction, I have here, say, the data set. This is the type of large images I could get on the life science sample. And we still, this is the resolution that is there together with the field of view. So, just for the sake of time, I will skip direct to here, to the last part, which is also, let's say, going to isotropic resolution. So, making use of those different techniques that I've just shown, it is now quite possible to go to really data sets which will show small and quasi-isotropic voxel size with actually pretty reasonable dimensions, and where, let's say, I can really rely on my data set not only to provide me a resolved image, say, in the main SEM plane, but also you could say this is a data set that is just being looked into, let's say, from the side, so from let's say realigned stack of slices, and where you can really get to see extremely let's say resolved data. Just looking at this one also in higher resolution, just to give an idea, let's say, how far this is. And yeah, eventually this will be reconstruction. So this will basically lead to, let's say, my conclusion, and really, let's say, also, let's say, give an order of magnitude where DualBeams can go to with these type of techniques. Where, I mean, we've seen it, let's say, from a voxel resolution, we can really go down to the 5 by 5 by 5 nanometer resolution, and possibly below. Let's say, with the new techniques, also access much larger volumes that were previously available, and therefore, again, extend the complementarity to other techniques that are available. So, with this, I mean, I'd really like to, let's say, conclude this presentation by saying, well, I mean, there's definitely plenty of room for already acquiring a number of data, but I mean, this is far from, let's say, collecting all of them. I mean, there's tons of other ideas, like I mentioned, that are quite possible. And let's say, moving forward, there's definitely a lot more things that could be, let's say, thought of. But there, I mean, most important is will also be, like we've done in the past many times, to, let's say, further interact, let's say, with you and let's say, with other people involved in 3D, just to so that the technology can continue to progress in this direction. So with this, I'd like to thank Gary for let's say, this opportunity and any questions.
Could you comment a bit on how you actually measure this slice thickness?
I can let's say, explain some of it. I have to say I don't know all the details, but this is basically let's say top-down measurements that are made by let's say the focused beam at let's say higher magnification. So we take actually let's say shots at every slice that we cut at let's say sufficient magnification, so that we can truly measure let's say what the distance is going to.
So you take it from the three-point view.
You made a comparison to making fusion marks that are at an angle, and you measure the space in the image plane.
I'm not sure if we have a comparison to that.
It would be a relatively simple experiment.
Yeah, correct.
James?
On your second to last slide, when you're kind of showing the size scales for using FIB-SEM, your volume sizes are getting pretty large there, and this is more just a question of using, I think, the second highest current to do our slicing, and we're only, you know, it's about like a 50 micron by 50 micron cube, which I think gets you around 50,000. So, I mean, for these very large volumes, you know, even a factor of 10 larger than that, do you have plans to increase the capability of the current for milling?
Yeah, there's definitely, let's say several plans, you could say, because let's say this kind of problem can be approached from many different angles. But as far as you could say purely field-focused findings are concerned, you could say step number one, which is the one that rolled out actually just a few weeks ago, is just, let's say, the traditional ways of, let's say, boosting your optics, so that you still get a relevant beam, but where you will still be in the area of, let's say, 60 nanoamps or something like that. If that is not sufficient, say, the next step that is being worked on, unfortunately not yet as a rule, but hopefully soon, will be really to switch to different type of ions and of ion sources. Maybe that's something we've seen presented, and where we're going to make use of what we call plasma field, which this time can deliver up to a microamp of current. So in principle, yeah, more than enough. But then we'll, let's say this is, let's say, I don't want to speculate extensively on this, mainly because, let's say, as far as 3D applications are concerned, that we don't necessarily completely know yet what to expect from this. Simply because, say, results could be equally good, since, let's say, even let's say, the precision of the slice that you can expect not only depend on the quality of the beam, and even say less on the quality of the beam than the profile itself of the beam, and how you can say finely position it to make fine slices. So this is something we'll have to see. I mean, here let's say we'll probably still do let's say more of a year before we start seeing this kind of technology applied to 3D applications.
Yeah, Laurent also from EMPA. My question is a little bit in the direction of low. You mentioned low kV backscatter imaging. I know we have a Nova NanoSEM from FEI. So in the SEM we have this VCD detector which works very nice. Is there a similar thing for DualBeam FIBs, or I mean, you have problems. I think when you have two beams, there is a problem with the space, yeah. And another problem is, of course, when we go to magnetic materials. So can you comment a little bit on this?
Sure, absolutely. Well, let me answer, let's say, in two parts, because there's, let's say, multiple questions in here. So, is there a way beyond the Nova NanoSEM? The answer is obviously yes, there is. And even within DualBeams, you could say, compared to the Nova NanoSEM, let's say since let's say last month, we are now almost 2 generations away in terms of in-lens detector technology. So there has been, let's say, quite a lot of effort. First of all, on the in-lens detector to let's say, well, improve the collection, do filtering as well. So that's pretty much covered in the DualBeam like the videos. Now, why do we do this? Obviously, let's say, like you said, we could make use also of solid-state detectors that go below the lens, but they're large. They're not necessarily as handy to use in DualBeam for 3D applications. So we still always, let's say, look from both sides and keep improving, let's say, both on the in-lens detector and below the lens detector, just to meet the needs of the applications. Now, let's say on the magnetic materials, I mean, this is also the reason why, let's say, a lot of effort was invested in, let's say, improving the imaging without necessarily using commercial lenses. So that's also something that, let's say, Helios nowadays can do well for.